Okay, so this is the last video for section 4.1, part 4, and we are going to look at tables. The following table shows examples of linear and exponential functions. So we want to differentiate which is which. So at first you can pretty much tell right here from, how the layout is, but we're going to look at why that is and then see if you can do it on these charts below in number 6. So first we have all our x values right here, and they're going to work for each of these y values. Okay, so first, just kind of ignore what's over here and focus on this section. Okay, so we're looking at this 3x plus 7. You can tell that's in mx plus b. But let's look at what happens in between here. So going from each unit, so you have to pay attention how far apart these are. So let me get rid of some of this stuff here. If you look at my x units, they are 1 unit apart, right? So I'm adding 1 on the x part, and then I'm adding 3 over here on the y value. So these are my y's, okay? So as x goes up 1, y goes up 3, and so on and so forth. That's happening all the way throughout this. Always repeated addition of 3. So that tells me it's a linear pattern. That is repeated addition. We can look at the y-intercept is 7, and we can notice right here in this row, all in here is my y-intercept row. Okay, so that'll hold also for the exponentials. So let's look at the next one where we have this as my y value. I have a base of 2, and then I have a repeated factors of 3. So 3 to the x. So that tells me that there's some repeated multiplication going on, which will be an exponential pattern. And we can just double check that. So 2/9 times 3. So this is times 3 is going to give me the 2/3, and so on and so forth. So I'm multiplying by 3 every time. So that's an exponential pattern. And then we have negative 2x plus 1 over here. Oh, I also want to point out on the exponential pattern, I did say the base was 3, but the y-intercept is 2. That's that value right there. On this one over here, we have the negative 2x plus 1. So my guess is my y's are going to decrease by 2 each time whenever my x's go up by 1. Now you do have to note, like this table here, I had a consistent increase of 1 each time on my x's, but on some of the tables below, it doesn't work like that. It'll be like every 2. So you have to pay attention to what the x is doing as well. So this one's just a simple decrease by 2, so that's going to be linear. Now we have our back to this exponential looking equation, right? So we have a half to the x, so I'm dividing by 2, or actually multiplying by half, so we can still always say it's repeated multiplication. So that's going to be times a half, and so on and so forth. And my y-intercept would be the negative 3. When x is 0, this whole thing is going to go to 1 times negative 3 is negative 3. So that's an exponential pattern. So now if we just have the table, can you come up with the equation or function that will represent that? So you got to figure out, what's my pattern? Is it repeated addition or subtraction, hence linear, and going to be y equals mx plus b form? Or is it going to be repeated multiplication and going to be the exponential pattern, y equals a b to the x? So let's try that. I think these two actually are pretty straightforward. We have our increase of 1 each time. That's looking pretty normal. So I want you to pause and try these and see if you can find the equation. I think the two below here, they're a little trickier. Go for it if you want to try them on your own, but pay attention to the X column. So the one on the left here is linear. It just increases by 4 each time for the Y's, by 1 for the X's. So I also am given my y-intercept in the table. So y equals 4x minus 1. The one on the right, I can see that easier if I change my y values to improper fractions and then multiply them by 2 is how I can clearly see that pattern, right? So I know my base is going to be 2. My exponent is x, but how did I figure out the y-intercept? Because it's not here on my chart. Well, a couple of different things I could do. I mean, I could backtrack it, right? I could just kind of reverse and figure out what it is for, if I put 1 in here. Let's just get these out of the way. And if I just kind of change my table a little bit here and put a 1 and then put a 0, figure it out that way, I could do that. If I'm multiplying by 2 when I'm going up, to reverse that, I would just have to divide by 2. So this would end up being 2/3 here, and this would end up being 1/3. So that would be my initial value, or y-intercept, right? Another thing I could do is, if I didn't know this yet, and I was just saying that's going to be some a, just like we've done with linear functions and some other things that you've had to pop in to figure out values for, like the functions like for quadratics and the polynomials and things like that. The technique used would be to pick a couple values here. So say I just pick this one, right? 3 and then 8/3. So I would put 8/3 for y. I would leave a by itself. I would put my base 2, and then x is 3. So I would calculate out what that is going to be. So that would be 8a. And then multiply both sides by the reciprocal here of, 1/8, or divide by 8. And then we would end up getting 1/3 equals a. And pop that in here. So that's the answer for those first two. So depending what it is, if you just have a little table with a couple to go, you could use this technique. But I really like this one because you're going to have to do that in some word problems down the road. And you might as well kind of get some practice with that skill now before you're having a word problem too. Now the next couple here, we have a different situation, because if you look here, I have 2 units in between. This one I only have 1, and this one I have 4. So you have to really take those into account when you're doing this. But you actually can just look at these 2 points and see how they relate together, and if there's a normal pattern happening, or if it's something a little more unique. But I can write these over 2 to help me out so that it just matches. So that would be 6/2, and this would be my 10/2, okay, for these two. And if I think about what's happening is between these two, I can clearly see that I've added a half. But this one, I actually added 4 halves, right? But look at my leap over here is 4. So that's why I've added a half 4 times. So it's still repeated addition. You can even look at it this way if you wanted to see, does it fit a slope pattern like a linear? You could do it as the 5 halves minus 3 halves over 1 minus -1 for my x's over here in the x column. And I would sort that out. It would be 2 halves, which would be 1, over 1 minus -1 would be 2. So that all is in alignment and matches up. So no matter which method you use, you can figure that out. So 2x plus 2. And then you can check it. Just put some points in to double check. And how did I know? Oh, kind of jumped the gun there. I should be half x plus b. Again, you could kind of figure out what this is in between here. What would go there would be 4 halves, which would be 2, or you could plug values in just like we've done in the past. You know, pick any value, pick like 5 equals a half times 6 plus b, and figure out what b is. Well, it'd be 5 minus 3, 2 equals b. So then we would put that back up in here, and that would be our linear equation. The one on the right is just a little trickier. You might want to pause that and play around with it a little bit, see what you come up with and if you can get the right idea for it. But again, notice there's not single units here. There's some gaps here and here, but this is a single unit. So you can kind of fill in the empty spots in the table if that helps you, or just try playing around with it and see, and then I'll go through it. So go ahead and pause the video and do that as classwork. Okay, so hopefully you've tried that one. A couple of things to note. I do have the y-intercept, so I'm happy about that. So I know my setup is going to be y equals something. Is it linear or is it exponential? Well, just looking at this, I'm gonna guess this is probably exponential, but let's see. So if I look here, 5/9, in order to jump up to, this is the 1 unit that I'm looking at, right? Plus 1 unit on the x's, so I can just have an easier picture. Then I would notice that I'm multiplying by 1/3, right? I'm not adding that. I have to multiply in order to make that leap. But on this one, it's kind of a little bit different. It's a little weird because I'm actually multiplying by 1/9, right? But it's when I have 2 units between my x's, and that kind of happens here and here. So let's check that out. So I also have 1/9 for every 2. So 1/3 for every 1 versus 1/9 for every 2. Well, that's really the same thing. But what I want to make sure I notice is that it's definitely an exponential pattern. But if I take this root here and just look at these first ones, let's start there with that. I would have y equals 5 is my initial value. My base, let's use the 1/9, but that's for every 2 x's. Okay, or does that actually equal this same thing here? Y equals 5, 1/3 2x. Can I say either one of those is okay? Hopefully you catch on that you can do that, right? Oops, sorry, I should not say 2x. It's for every 2, so it's x over 2. So make sure we do that. We're skipping every other one. So it should be x divided by 2, right? So if we look at 1/9, and if we were to kind of break this apart, 1/9 to the half would be 1/9 to the 1/2, or square root of 9, which is 1/3. So that would be an equivalent thing to say if we kind of split that apart. So either way, you can address it and you would be correct. Okay, so this is correct and this is also correct. So I hope that helps you get the gist. You'll see some of those in your electronic homework and a few on your paper homework as well. Have a great day. Thanks for watching. That's the end of the 4.1. We'll do the shapes of graphs next in 4.2.